Add binary. You'll see add binary in countless screens because it blends string manipulation with bitwise thinking. No big integer shortcuts. If you can narrate carries clearly under pressure, you instantly stand out. Today, we'll solve it with BASIC so you can speak the logic and code it smoothly in one pass. O(n plus m). Time, 0 drama. Breakdown. We're given two binary strings A and B. We must return their binary sum, also as a string. We'll add from right to left, track a carry, and handle unequal lengths and a final leftover carry. Assess. Digit by digit addition is perfect. Each step adds bit underscore A plus bit underscore B plus carry. The next bit is sum %2, and the new carry is sum //2. This runs in O(n plus m), and uses output size space. We avoid converting to big integers, which some interviewers prohibit. Structure. Plan. 2 pointers I and j at the ends of A and B, a carry equals 0, and a list out to collect bits. While any pointer is valid or carry is 1, grab bits, 0 if out of bounds, sum, push sum %2, set carry equals sum //2, move left. Reverse out at the end. Solution 1, using Python conversion time complexity, O(n plus m), for conversion. We begin by defining a class named solution. This simply organizes our method in a clean structure. This defines our function add binary, which takes two binary strings and returns their sum, also as a binary string. This single line does all the work, and here's the breakdown. Int a(2) converts string a from binary to a normal integer. Int b(2) does the same for string b. We add the two integers together. Bin converts the sum back into a binary string, but Python prefixes the result with 0b. 2 slices off the 0b part, leaving only the clean binary digits. This approach relies heavily on Python's built-in conversion tools. The time complexity comes from converting the strings to integers and back, which takes O(n plus m). Final wrap-up. And that's how this algorithm works. It first lets Python convert the binary strings into integers, then adds them and converts the result back to binary, trimming away the formatting prefix. Efficient, simple, and elegant. Test case check. Add binary. Int bin approach lets test our function using this input, a equals 11 and b equals 1. These strings represent binary numbers, so 11 is 3 in decimal, and 1 is 1. Here's why the solution works. We convert both binary strings into integers, add them together, and then convert the result back into binary. Python's bin function gives us a binary string with a 0b prefix, so we slice it off with 2. And that's exactly what our program outputs, 100. It matches the expected result perfectly, showing that the binary addition is handled correctly. Wrap up. So, our implementation is correct. The algorithm successfully converts binary inputs, adds them, and returns the proper binary output. Simple, accurate, and reliable. Solution 2. Manual bit-by-bit addition time complexity. O max len A, len B. We start by defining a class called solution. It simply organizes our binary addition method. This defines the function add binary, which takes two binary strings and returns their sum, also as a binary string. We create two pointers, I and j, starting at the last index of each string. This lets us add the binary digits from right to left, just like how we add decimal numbers starting from the ones place. We initialize a carry value. If adding 2 bits goes over 1, we'll carry the extra into the next position. We create an empty list called result, which will store our resulting bits as we compute them. We begin a loop that keeps running as long as there are bits left in string A, or bits left in string B, or we still have a leftover carry. This loop runs at most max len A, len B, times O(n). We read the current bit from string A, unless we've run out of characters, in which case we treat it as 0. Same idea for string B. If the pointer is still valid, grab the bit. Otherwise use 0. We compute the total sum of the 2 bits plus any carry. For example, 1 plus 1 plus 1 equals 3 or 1 plus 0 equals 1. We update the carry. In binary, totals 0 or 1 give carry 0. Totals 2 or 3 give carry 1. We append the resulting bit, either 0 or 1, by taking total %2. This gives us the current bit of the sum. We move the pointer I one step left to read the next bit from string A, and we move pointer j one step left to read the next bit from string B. Finally, we reverse the result, because we built it backwards, and join it into a string. This gives us the final binary sum. Final wrap-up. And that's how this algorithm works. It first sets up pointers and a carry, then adds the bits from right to left while updating the carry and building the result, finishing by reversing everything to get the correct binary number. Efficient, simple, and elegant. Test case check, add binary, manual addition with carry. Let's test our function using this input. A equals 1010 and B equals 1011. These strings represent two binary numbers that we want to add together bit by bit, just like doing binary addition by hand. Here's why the solution works. We process each number from right to left, adding the bits along with any carry from the previous step. Each time, we calculate the sum of the two bits, the new bit to store, and the next carry. And that's exactly what our program outputs, 10,101. It matches the expected answer perfectly, showing that our manual bit addition logic handles carries and alignment correctly. Wrap up. So, our implementation is correct. The algorithm successfully adds two binary numbers digit by digit with full carry handling, efficient, accurate, and reliable. Add binary. Let's do a recap. If you can explain carries under pressure, add binary becomes a flex. It blends string handling with bitwise thinking, no big integer shortcuts, so it's perfect for showing clarity, control, and speed in interviews. Breakdown recap. We're adding two binary strings and returning their sum as a binary string. The core idea: add from right to left, keep a running carry, and handle different lengths plus a possible final carry at the end. Assess recap. We compared options and chose digit by digit addition. At each step, we combine the two current bits with the carry. The new bit comes from the remainder, and the carry comes from the quotient. This gives linear time in the total length of the inputs and uses only output size space, exactly what interviewers expect. Structure recap. We set two pointers at the ends of the strings, track a carry, and loop while there are bits or a carry left. Each step: read bits, or 0 if out of bounds, add with carry, record the current result bit, update the carry, and move left. Finally, flip the collected bits to get the correct order. Implement recap. We followed that plan precisely and ran it on LeetCode. Smooth execution, no conversions to big integers, and no edge case surprises. One pass, clean logic, and fully compliant with interview constraints. Check recap. We verified the behavior across typical and edge inputs, different lengths, all zeros, long carry chains, and everything matched expected outputs. All LeetCode test cases passed. Closing insight. The big takeaway? Master the carry. Once you can narrate read, add, write bit, update carry, move left, you'll handle binary arithmetic, base conversions, and many pointer-based string problems with calm, reliable precision.